Assalamualaikum and hi everyone. We are from University Tun Hussein Malaysia. Let me introduce myself first. I am Nur Husna binti Muslim and I'm honored to present to you our research titled Adsorptive Removal of Phosphorus from Water using raw Lala clamshells as adsorbent, kinetic, isotherm and contour prediction studies. This work was carried out with my team members Dr. Nurul Hudai, Madam Nur Zainaria, Technologist Nur Amy Nadia, and Madam Siti Maisara. These are the main outlines of our presentation. To begin, let's take a moment to look at the environmental challenge eutrophication. This harms water quality and aquatic life. It starts with agricultural runoff, where excess phosphorus from fertilizers enters water resources. This leads to algal blooms turning clear water green. When the algae die, bacteria decompose them, using up oxygen in the water. As oxygen drops, aquatic life dies. Hence, our innovation targets the root cause by using raw Lala clamshells for phosphorus removal. Now, let's move on to the graphical abstract. Raw Lala clamshells were collected, rinsed, dried, and sieved to a particle size of 1.18 to 2.36 mm. These were then used as natural adsorbents in batch experiments to remove phosphorus in water. Phosphorus levels were measured using a DR1900 portable spectrophotometer. These are the key findings from our study. Moving forward, this slide outlines our product description. These are the photos of our product. Our innovation repurposes Lala clamshell waste into a natural adsorbent for phosphorus removal in water. These shells contain up to 95% of calcium carbonate, known for its high effectiveness in binding phosphorus from contaminated water. Let's look at what makes our innovation unique. It is the first study using raw Lala clamshells for phosphorus removal. We apply a waste-to-resource approach by turning waste shells into valuable adsorbents. We also use scientific analysis and predictive modeling to enhance its performance. Now, let's look at how our innovation benefits society. First, it improves water quality by removing excess phosphorus. Second, it controls eutrophication by reducing nutrient pollution. Third, it offers a cost-effective solution using low-cost shells. Next, we'll talk about the current status of our product. As shown on the slide, our innovation is currently at TRL5, indicating that the integrated system has been successfully tested in a laboratory setting. Now, let's explore the commercialization potential of our innovation. First, it is cost-effective as it uses waste materials. Second, it shows proven performance, achieving 64.2%. Next, it is also eco-friendly and has strong market potential, especially in industrial water systems. Let's look at the benchmarking analysis shown on this slide, comparing our solution with chemical treatments. First, for phosphorus removal, both methods are effective. For cost effectiveness, our solution clearly stands out. In terms of sustainability, our innovation promotes waste reuse without adding harmful chemicals. In summary, our solution is the best option. Next, here are the potential industry partners for commercialization. First, Indah Water. Our product can be applied in municipal wastewater treatment. Second, Senviro. They can adopt our product for industrial wastewater treatment. Last, MGTC. We aim to obtain My Hijau certification for our product as a recognized green solution. As shown on the next slide, our study aligns with three main SDGs. First, SDG 6. Our product removes phosphorus from wastewater, hence improving water quality. Second, SDG 12. We reuse seafood waste by turning Lala clam shells into a useful adsorbent. Last, SDG 14. By reducing nutrient pollution, our innovation helps prevent harmful algal blooms and protects marine ecosystems. To validate our findings, we conducted several scientific analyses. First, XRD analysis confirmed the shells contain 100% of aragonite, which supports phosphorus adsorption. Second, SEM analysis showed surface changes from rough and uneven to fibrous after phosphorus adsorption. Third, EDXRF analysis revealed an increase in calcium and oxygen, showing oxidation process. Last but not least, FTIR showed changes in functional groups, including a phosphorus phenyl peak. Let's take a closer look at our adsorbents performance. On the left, the graph shows adsorption capacity in milligrams per gram. At 8 grams, the capacity reached 0.0818 mg per gram with equilibrium at the minute of 1440 and became stable at the minute of 4320. On the right, the graph shows removal efficiency percentage. At 10 grams, we achieved 64.2%, also the minute of 1440, which remained constant after the minute of 4320, confirming full adsorption. To better understand the adsorption process, we used kinetic, isotherm, and contour prediction models. Firstly, the kinetic model follows the pseudo-second order, indicating chemisubtion. Secondly, the isotherm fits the Langmuir model, showing monolayer adsorption on a uniform surface. Last, the contour prediction diagram shows how adsorbent mass and phosphorus concentration affect efficiency. For example, to remove 20 mg per liter of phosphorus, 6 grams of raw Lala clam shells are required, achieving 40 to 60% of removal efficiency. Listed references in this slide ensure our study is well supported. Beyond its scientific and commercial value, our innovation is officially copyrighted. In addition, we have submitted our study to Jurnal Kejuruteraan, a Scopus indexed journal. Before I wrap up, we are especially grateful for the funding received under the MDR and GPPS grant. Finally, this project has contributed to talent development. As a master's student at UTHM, I have been involved in all stages, from experimental design to data analysis. Thank you everyone for your attention and making this work successful.
Wow.